Hi class, these are the notes for IM1, Integrated Math 1, Lesson 1.2, Geometric Sequences, and today we'll be looking at making a table, graph, and the recursive equation. This will be very similar to my last video on Lesson 1.1. The difference is today we're looking at a geometric sequence as opposed to an arithmetic sequence from 1.1. So if you haven't watched the lesson for 1.1, you might want to go back because I'm going to kind of go quickly through a few things that I explained more in 1.1. All right, so a geometric sequence is a sequence of numbers where to get from the first number to the next number to the next number, we're going to be multiplying to get to the next number instead of adding or subtracting like we did for arithmetic sequences. So if we look at our term number and our term value, the first term is 2, the second term is 4, the third term is 8. If we put those numbers into our table, when n is 1, our value a sub 1 is 2. Our value for the second term is 4. Our value for the third term is 8. And then we want to look at the pattern. So how do we get from one to the next? Well, if you look at what's happening with the numbers, if I do 2 plus 2, I get 4, but then 4 plus 2 isn't 8. So we're not adding here, we're actually multiplying by 2. So I'm going to do times 2 each time, and this is what we call the common ratio. So with an arithmetic sequence, it was a common difference, but now it is a common ratio. We use an R for common ratio, so our R is 2. If I go forward another one and I multiply by 2, I can get the next term here, which would be 16. Oops, 16. And then I can also go backwards by doing the opposite of multiplying by 2. I can do dividing by 2, and 2 divided by 2 is 1. So I can get my 0 term as 1, which gives me my y-intercept. A sub 0 is the same as the y-intercept. We looked at that a little bit in section 1.1. All right, so if we now graph our points, 0, 1 is going to be a little difficult to graph. Let's see if I can zoom in here. So 0, 1 is going to be about right there. 1, 2 should be here. The point 2, 4 is here. Sorry, my battery saver just turned on. 3, 8 goes here. And 4, 16 is here. And if you notice, this is a different graph than what we saw for the arithmetic sequence. In the arithmetic sequence, we had a linear function and it was a straight line. And this one definitely has more of a curve. I can then find the next term. If I want the 5th term or the 6th term, I can continue that pattern of multiplying by 2. And my graph goes up pretty high, so I should be able to do this a couple more times here. So 16 times 2 is 32, and 32 times 2 is 64. So let's put those points on the graph as well. So my 5th term is at 32, so I should have a point here. And my 6th term is up at 64. So we can really see how this grows in a curved pattern, not a linear pattern. And this is what we call an exponential graph or function, which we're going to explore more in our next unit. But definitely is different than a linear function. So geometric sequences create exponential curves. All right, so we talked a little bit about what n and a sub n represents in the last section, 1.1, but just really quick, n represents the term number and a sub n represents the term value. So I talked about it a little bit more in 1.1. The pattern here is that we multiply by 2 to get the next term value. And the shape of the graph is definitely curved, and it's exponential. All right, so now we get back down to the recursive equation. So it's very similar to what we saw in section 1.1. The next term value is going to equal the previous term value times 2, because that's our pattern in this problem. We saw it with arithmetic, it was always plus or minus a number, but now it's times 2. If we use our sequencing notation, that would mean that a sub n equals a sub n minus 1 times 2. And again, I explained more about what a sub n and a sub n minus 1 is in section 1.1, but just really quick here. If I, let's get a pink here. If I have a sub 6, then that's going to equal a sub 5 times 2. And if you notice, the 6 and the 5 are 1 away from each other. So if this is a sub n, if n is 6, then n minus 1 would give us that fifth term, a sub 5. So that is why we use a sub n and a sub n minus 1. All right, we'll do one more example. This one's a little trickier because we do have it going down. It's a decreasing geometric sequence. So let's see what that looks like. All right, so my term number and my term value, I always start with the first term when it's listed like this with commas, second term, third term. So my term when n is 1, I have 100. When n is 2, I have 20. When n is 3, I have 4. So I put my values into the table. Now we have to find the pattern. Now, if you look, it's going down by a factor of 5. And what I mean by that is to get from one to the next, we would divide by 5. 100 divided by 5 is 20. 20 divided by 5 is 4. But the problem is we have a little bit of a curveball here. The common ratio has to be a value we multiply by. So I can't say that the common ratio is dividing by 5. What I have to do is I have to change the division to multiplication. And when we do that, we have to remember that dividing by an integer is the same as multiplying by a fraction, where that number that we're dividing by goes in the denominator. So my common ratio actually ends up being 1 over 5. So let's see, just a little note. Dividing by 5 is the same as multiplying by 1 over 5. All right, so we have to use that multiplying factor when we do the common ratio. It's super important that we change it to a multiplier instead of using division. So instead of doing divided by 5, I'm going to say it's times 1 over 5 to get to the next term. So we've got 4 times 1/5 would be 4 over 5. You can always write that as a decimal, which would be 0.8, but I'm going to leave it as a fraction. I like fractions. All right, and then if we go backward to my 0 term, I have to think about what number times 1/5 is 100, or what number divided by 5 is 100, or lots of different ways to think about this. Or we can go backwards. Instead of dividing by 5 going forward, I can divide or multiply by 5 to go backwards, which I think is probably the easiest way to think about it in this case. So 100 times 5 would give me 500, which in this case is not going to fit on my graph, but that's okay. All right, so let's look at our graph. Here we've got a little bit more of a problem. I didn't make the graph quite big enough. The first term is 100, which is off my graph by a decent amount. So I'm just going to start with the second term. When x is 2 or when n is 2, a sub 2 is 20. But if we think about that first term being 100, I would want to go 20 above 80. So it would be somewhere up here at 100. Ooh, it's not letting me write. There we go, 100. So it's something like up here, just to give us an idea of how high that goes. So when we draw our curve, if we were going to connect the dots, we wouldn't cross over too soon. All right, and then I can go forward. When n is 3, we have 4 as our a sub n value. When it gets to 4, we have 4/5, which is a little hard to do, but it's a little less than 1. So something like that. You can kind of see it curve down. I'm going to stop there. If we kept going, the fifth term, if I took 4/5 and multiplied it by 1/5, the denominator gets multiplied by 5. So I would end up with 4/25, which is a small decimal, and it would be a little difficult or very difficult to draw my graph. So I'm going to just leave my graph the way it is. All right, and then let's see, what is the pattern? So we're going to multiply by 1/5 to get the next term value. You can explain it saying we divide by 5, but it's really important, again, to understand that the multiplier is 1/5, because when we do our explicit formula later, we're going to want that multiplier value. All right, the shape of the graph is curved. It's decreasing exponential. And then what is our 0 term? So a sub 0 we figured out at the top by going backwards. A sub 0 was 500. And where would that be on the graph? It would be the y-intercept at the point 0, 500, which definitely will not fit on my page. And then the recursive equation, again, if I write it out in words, the next term would be the, whoops, I spelled that wrong, would be the previous term times 1/5. Or we can write a sub n equals a sub n minus 1 times 1/5. This is the preferred way to write it using our sequencing formatting or notation. All right, and that is it for our geometric sequences.